All right, so last class we talked about most of the concepts related to hypothesis testing. And here's, let me just try to refresh your memory just quickly. Okay? So we have rejection region on both sides. Apparently this is a two-tailed test. Okay? And in order to come up with the rejection region and the critical value, well, critical value is the z-score which separates rejection region from non-rejection region. Okay? And you determine you find the z-score or critical value based on your alpha level. Okay? So apparently in this example, you decided to use 0.05 as your alpha level. Right? So you're going to assign half of 0.05 on each side, right? Upper tail and lower tail, and find the rejection regions that way. And then you calculate your test statistic. And anytime your test statistic falls within the rejection region, like here, right? Apparently your test statistic came out to be negative 2.0, right? And that falls right here in the lower tail rejection region. Okay? Then you're going to reject the null hypothesis. Okay? And are you 100% sure about that decision? I mean, in this example, your decision rule is reject the null hypothesis anytime your test statistic falls within the rejection region. Okay? And what do you think about that? Is there any possibility of error in that decision? If there is any possibility of error, what kind of error can you be committing by making decision that way? All right, let me make it simple. Type 1 or type 2? Type 1, okay? Because you are rejecting the null hypothesis, right? So if you are making any error by rejecting the null hypothesis, that means you are rejecting the null hypothesis when in fact the null hypothesis is true, right? That's type 1 error, right? Type 2 error is the error of accepting the null hypothesis when in fact it is false, right? So in this class, we have decided that we're going to avoid committing type 2 error by not accepting the null hypothesis anyway, right? So even when your test statistic is found within this non-rejection region, right, we will simply say do not reject instead of accepting, right? That way we can avoid type 2 error, okay? All right, so those were the major concepts that we covered so far. Today, I'm going to introduce you another way, slightly different way to make a conclusion in this hypothesis testing. Okay? It's called the p-value approach. Okay? The previous approach is called the critical value approach because we use the critical values to separate the rejection region and non-rejection region, and we made the decision that way. Right? In order to do that, you have to use the z-table and find the critical value, right? So if you want to use alpha level of 0.01 or 0.05, what should be my critical value, right? And you need to go to the z-table and find that critical value. Yeah? If you use p-value approach, you don't need to do that. Okay? So it's actually, in reality, in most of the actual real-life researches, right, nobody uses critical value approach. Okay? Everybody uses p-value approach. Okay? It's very convenient, so please pay attention and learn how to do that. Okay? The p-value, the formal name is observed level of significance. Remember, alpha was the level of significance. Okay? P is observed level of significance. Okay? And the definition is there. It's a probability of obtaining a test statistic equal to or more extreme than the observed value. But I tell you, forget about that definition. You don't have, it's a little bit confusing to understand that definition. Okay? What I prefer is this, this statement written in blue. Okay? P-value is the size of the area outside the test statistic. You can just remember that, right? It's a lot easier to understand, right? So, okay. In the critical value approach, we found the critical test z-score, right? And by assigning, say, 0.025, right, area, okay? And that means whenever your test statistic, suppose your test statistic came out to be here, right? In the previous example, it was 1.96. Critical value was 1.96, but your test statistic was 2.00 on the other side, but you know, doesn't matter, right? And your conclusion was reject the null hypothesis, right? Okay. In p-value approach, what we're going to do is, okay, here's our test statistic. And we found out it's 2.0, right? And we're going to find out the size of the area outside the test statistic, right? So this yellow area, yellow shaded area, okay? And let's say that's actually half of P, right? Because we're going to do the same thing on the other tail, okay? Critical Z of negative 1.96, and here's a test statistic of negative 2.0, right? And so here, so p-value is the area, total area outside the test statistic, right? So this area plus this area, right? So you can say this is half of p, and here's another half of p. Right? Right? So let me ask you this question. Now we know that this yellow size of this yellow shaded area, if you add them up, that's the p-value. That's the size of the p-value, right? What about this white shaded area? What can you say? This one, what is this? Yes. This white shaded area, that is, in our example, 0.025, I told you, right? But that's half of alpha, right? And here's another half of alpha, right? So when you add them up, the total size of the white shaded area is alpha, okay? Well, between alpha and P, which one is larger? Alpha is larger. Why? Because our test statistic is right here, right? So apparently the yellow shaded area here is smaller than white shaded area here, right? Because the test statistic exceeded the critical value, right? If our test statistic was here, suppose, instead, okay? If our test statistic was there, then our p-value would be this, or half of p, right? So in that case, p will be larger than alpha, right? So you have to understand that relationship, right? So if the test statistic in two-tailed test, if the test statistic was greater than critical value, or the test statistic was less than negative critical value, right? Then what is your conclusion? What should be your conclusion? You're running the two-tailed test and you found out either this one or this one, right? Then your conclusion should be reject the null hypothesis, right? Reject the null hypothesis, right? But then, if this is true, then we find out that the p is less than alpha, right? Because the test statistic exceeded the critical value. The size of the area outside the test statistic, yellow shaded area, right, would be only that much, and the white shaded area, which is half of alpha, will be larger. So p-value will be less than alpha. Okay? So here's a decision rule. When you use a critical value approach, you state null hypothesis, alternative hypothesis, test statistic, decision rule, conclusion, and interpretation. I told you, right? You have to have those 6 components, right? And the decision rule would say if the test statistic is either greater than critical value or less than negative critical value, you will reject the null hypothesis, right? If you're using p-value approach, all you need to say is this. If p is less than alpha, reject the null hypothesis, right? And we are doing the same thing, right? You see that consistency? Okay? It's the same rule as this one, okay? How is it more convenient? Well, these days we use computer to, we just provide the data to the computer, and computer calculates all the test statistic, right? And when it calculates the test statistic, it also calculates the p-value, the area outside the test statistic, right? So in practical research, whenever we get the output, right? You run the regression, okay, and get the output. First thing you look at is p-value, right? And just to see whether p-value is less than alpha or not, right? Who decides alpha? Yourself. That's right, right? Researcher himself or herself sets the alpha level. In other words, you decide what level of risk you're willing to accept for type 1 error, right? Again, why do you have to accept the level of risk? I mean, risk of type 1 error? Can't you just eliminate the probability of error completely? What was the answer? Huh? Is there any way you can eliminate the error completely?
You don't have a way to eliminate the total probability of error because we can't make this whole sampling of the population.
Right, right. The only way you can eliminate possibility of error is if you can use the entire population, right, in your calculation, right? But the whole problem of the statistic is we cannot do that, right? It is impossible, either impossible to use population or it's just too costly, right? Costs too much time or money, right, to use the entire population, right? So we are selecting sample, right? And since we are selecting sample and we are making the conclusion based on sample outcome, right? You have to accept, you have to allow certain percentage of error, right? The probability of error, right? And it's up to you, right? Whether you want to accept the 1% possibility or 5% possibility, right? It's up to you, right? Anyway, so yeah, that's the difference between the critical value approach and the p-value approach. Okay? So here, if the p-value is less than alpha, reject the null hypothesis. If not, then do not reject the null hypothesis, right? All right, let me open open up my notes. Okay. So going back to the previous example that we used last class, here somebody claimed that the average number of TV sets in the households in the United States is 3, right? And you wanted to test that claim, right? So null hypothesis says mu is 3, alternative says it is not, right? And you decided the level of significance of, I don't know, was it 0.05? I think they used the 0.05, right? And then determine the appropriate technique. Well, in this example, sigma is assumed to be known, right? So we can use a z-test. So we can use the z-score as the test statistic, right? And we're going to talk about the other case later, a few minutes later, right? So your test statistic came out to be negative 2.0, right, when you calculate the test statistic. All right? So the next step is we have to find the area outside the test statistic, right? And how do you find it? Well, you have to use a z-table, right? Again, in reality, you use computer, and computer gives you the test statistic and the p-value immediately, right? But if you do it by hand, then you have to use the z-table, right? Okay. So here's here's a copy of the z-table that you see in the back of your textbook. Come on. What's so slow? Interesting. Can't even open the PDF file. Ah, here we go. Okay. And let's make it a little bit larger. All right. So here's the example of z-table. And if you look at this illustration, this shows, this table shows this green shaded area, in other words, the left tail area outside the corresponding z statistic, right? So our test statistic was 2.0 or negative 2.0, right? So if you go to negative 2.0 here, 2.00, right? Here, you know how to use the z-table, right? And that area is 0.0228, 0.0228, right? And that's how they came up with this value, right? The probability that z-score will be less than negative 2.0 is 0.0228, right? And that's half of p. And here's another half of p, right? So when you add them up, right? Add them up, the total p-value is 0.0456, right? So here's another convenience, another benefit or advantage of using p-value approach over using critical value approach. In the critical value approach, you set alpha level, right? And based on alpha level, you find the critical value, right? Like here, right? And you compare the test statistic to critical value, whether it exceeds or not, right? And you make the decision, right? If you use p-value approach, you don't have to use any of those set value like 0.05 or 0.1 or whatever, right? You can actually use multiple conclusion, right? Because what happens is, well, we found out the p-value here is 0.0456, right? So if you use 0.05 as your alpha level, Suppose you decided to use 0.05 as your alpha level. What should be your conclusion? Yeah. So using 95% level of significance or confidence level, right? What should be your conclusion? Because P is less than alpha, right? Well, alpha is 0.05, and we found our P value is 0.045, right? So your conclusion will be reject the null hypothesis, right? But what that means is you can use, what if you use 0.03? Suppose you, for some reason, you want it to be 97% confident in this test, right? Which means your alpha level would be 0.03, right? What will be your conclusion in that case? Do not reject, right? Because obviously P value is not smaller than alpha level, okay? So it's very convenient. I mean, once you know the P value, then you can see exactly what percentage, up to what percentage you can be confident, right? Say, I guess you can be, 90, you can be up to 95.4%, right? 95.44% confident, and you can still reject the null hypothesis, something like that, right? All right, when we learn the t-test, you will see the full benefit of that. Why, we bother with that, right? Okay, so here's so that was the example of the what was p-value approach, right? All right. Do you have your books with you? Yeah. Anyway, okay. So question A, basically it's asking for hypothesis testing, testing this claim at 0.05 level, right? So remember, if you see this kind of question in the exam, right, you have to list the 6 components, right? You start out with the null, alternative, yeah? So somebody claims mu is 375, right? And you want to test that hypothesis, okay? And the next component, test statistic. Assuming this is a correct calculation, I guess he got the same number, right? Okay, so first of all, it says the population standard deviation is 100 hours. So population standard deviation sigma is given, right? So we can use z test, or z as the z-score as the test statistic, right? So z is 350 minus 375 divided by 100 over square root of 64 is negative 2.00, I guess, right? All right, and the decision rule, right? For question A, apparently in question B, it asks for p-value. So in question A, you can use the critical value approach, right? And in order to use critical value approach, you have to decide the critical value. And we've used this kind of example many times, right? So if you are looking for this is a two-tailed test, right? So 0.025, 0.025. Then we know that this is 1.96 and this is negative 1.96, right? From the previous examples, right? Or you can go to, if you want, you can go to the Z table and actually look for 0.025 0.025 right here, right? 0.025, right? And you find out that's negative 1.96, right? That's how you use the z-table to locate the critical value, right? So you can say reject the null hypothesis if there's an easier way to do that. You can say absolute value of the test statistic is greater than z.025, which is 1.96, right? Then you covered both sides, right? Either the test statistic exceeds 1.96, or it is smaller than negative 1.96, right? All right, and then the next item is conclusion. 1, 2, 3, 4, 5, conclusion, right? Well, since the test statistic, the absolute value of test statistic is 2, which is greater than the critical value, your conclusion is reject the null hypothesis, right? And then the interpretation is what? What does that mean? Based on the context of this problem, right? Question asks, is there evidence that the mean life is different from 375? Well, what is your answer? Yes, because we just rejected the null hypothesis. Okay? So that means we have sufficient evidence to claim that the mean life is different from 375. Okay? You can write it out. We have sufficient evidence to conclude that the mean life of the light bulb is a light bulb? The light bulb? Something like that, right? Yeah, light bulb is different from 375, right? Okay, so that should be this answer to A, right? What about B? B asks for p-value, right? So you calculate the test statistic, came out to be negative 2, and the p-value is what? The area outside the test statistic on either way. We're running the two-tailed test here, right? So you have to set aside the, well, if this is 2.0, here's negative 2.00, right? And we have to calculate this area plus this area, right? Well, since the distribution is symmetric, all you need to do is find one side and multiply by 2, right? So for that purpose, you need the z-table. Again, in actual research, if you use a computer will give you the p-value, right? But if you're doing by hand, then here, 2.0 is right here, right? 2.0. And one side is 0.0228, right? So the p-value is 0.0228 times 2 is what? 0.0456, right? We did that in the previous example, right? Question, can you do this? Right? I hope you can do this, right? All right, so that was the example of how to do this, right? All right, here's the next topic for today, okay? So what if sigma is unknown, right? If sigma is unknown, in other words, if the population standard deviation is unknown, then what do you have to do? Well, you have to take a sample and calculate the sample standard deviation. We use S for that, right? Okay. So If for some reason, somehow, population standard deviation was known, then you could use z-test, right? But if this is unknown, then what you can do is take a small sample and calculate sample statistic, sample standard deviation, right? And then if you think about the sampling distribution, right? There's some variability. We use the sigma over square root of n if the sigma was known, right? But if sigma is unknown, and the only way to handle this is we have to replace it with sample standard deviation, right? Then what you have to understand here is this introduces a little bit more variability to the sampling distribution, because if sigma is known, then we know that. There's only one fixed value, like previous example, standard deviation, population standard deviation is 100, right? But if you have to use sample standard deviation, first time you take a sample standard deviation may come out to be 98, right? And then you take another sample and calculate the standard deviation. This time it may come out to be 1.101, right? Depending on how you select your sample. We have so many light bulbs in here. Suppose you produced 100,000 light bulbs yesterday or today, right? And you selected, say, only 100, sample size is 64, whatever, right? So you selected the 64 light bulbs out of 100,000 light bulbs and measured how long it lasts, right? So depending on what sample, how you selected sample, you can come up with 98 or 101 or whatever for the sample standard deviation, right? So what that means is this dispersion or spread or variability is a little bit larger. Right? You have to allow a little more variability in your sampling distribution. Okay? So, what that means is you cannot use a z distribution. Your sampling distribution is not going to be normally distributed, right? What can we do? Well, there was a guy named William Gossett, right? Okay. Do you remember anything about William Gossett if you were in my class last semester? Irish. Does it ring a bell? Where did he work? Guinness Brewery, right? You guys like Irish beer, right? It's a very dark, bitter beer, but I like it, right? I really like dark beer. Anyway, he was working in the Guinness Brewery, right? And apparently he had a lot of time on his hand. Maybe his job was just watching the beer brew, right? Mature, right? Anyway, so he introduced what we call T distribution. Okay? And without T distribution, today's statistics would not exist, right? What that means is science, right? Today's science will be quite different, right? We're not going to have this kind of advanced science, right? So his contribution to the world is really immense, incredible contribution, right? But he was so modest, right? He called himself student, right? So the full name of the T distribution is student T distribution. Student's t distribution, right? So student was his pen name, not real name, right? Anyway, so here are a few things you have to understand about the t distribution. Yeah? So instead of z statistic, we're going to use a t statistic, right? But that's exactly the same. The test statistic will be t instead of z, right? And the way you calculate the test statistic is exactly the same as before, except we use S instead of sigma. You're going to use S, sample standard deviation, right? And all the rest will be exactly the same. The way you run the test, right? You set up the null hypothesis, alternative hypothesis. You calculate the test statistic, right? And then based on if you're using critical value approach, right? Instead of z-score, you're going to use t-score for your critical value, right? And you make the decision that way, right? If you're going to use p-value approach, right? Then you can calculate the p-value, okay? And reject your decision rule will be reject the null hypothesis if p is less than alpha, right? Exactly the same as before. Okay? So the only difference is we instead of sigma we use S. So instead of Z table we're going to be using T table. Okay? Alright. So let me show you how T table looks like. Okay. Here's a T table. Yeah. If you look at this illustration, the number you are seeing here are actually T scores. Okay? So here's one thing you have to understand. The Z table and T table are completely different. Okay? If you remember, if you look at the Z table, right? On the margins here, on the first column and first row, you had Z scores, right? So for example, if you had Z score of 1.28, right? Then you would look for 1.2 here and 0.08 here. So if you come down here, that's going to be something like 0.8997, almost 0.9, right? So what you have on the margins are Z-scores, and what you have inside, the numbers inside, right, inside the table, these numbers are size of the area, right? That's the Z table. T table is completely opposite, right? The numbers you see inside here are not the size of areas, right? Those are the T statistics right here, T score, right? And the size of the area is found on the margins, right? For example, 0.75, over here, 0.25, 0.1, 0.05. It's hard to see a little bit, right? But here are the upper tail areas, okay? And for example, here, if you're looking for T-score, which has 0.05 in the upper tail area, the first number here is 6.3138. And all these numbers are actually the T-scores that have 0.05 outside that number, right? So how come we have so many different numbers here, right? Because the shape of the T distribution, I erased it, I guess. I told you T distribution is a little bit wider than the normal distribution, right? But exact shape of the T distribution depends on degrees of freedom. Degrees of freedom, okay? And for our purpose in this class, degrees of freedom so far in this hypothesis testing, right, should be n minus 1, Yeah? So for example, in this problem, if you have sample size of 64, right, then your degrees of freedom is 63. Okay? And so if you're looking for t-score or the critical value, right? For example, suppose you're running this test, right? This, yeah? And you're looking for the critical value with 0.025 on its outside, right? Then here 0.025 column is right there, this column, but then you have to come down to degrees of freedom of 63, because n is 64, n minus 1 is 63, and that is 1.9983, right? If you remember, when we were using z-test here, right, the critical value was 1.96, okay? So it was something like 1.96, right? But when you're running t-test, right, your critical value would be 1.9983, right? So a little bit outside here, 1.9983. So that's the z, and this is t. Yeah? I told you t distribution is a little bit wider than the z distribution, right? So on the z distribution, the number which has 0.025 outside is 1.96, right? But on the t distribution, the same 0.025, right? That number is 1.99, or almost 2.0, okay? So we have to use the t-table to run the test, right? And other things are exactly the same, right? Okay. Well, the problem is, how do you make the decision using p-value, right? If you remember, if you want to use p-value approach, okay, and if you're running z-test, right, you could, right here, if your test statistic was 2.0, you could locate the 2.0 here, 2.000, and you found out your p-value was actually 2.0, okay, was 0.0228, right? But on t-table, apparently we cannot do that, because on t-table, we have just a few t-scores given here, right? It's 0.0, the t-score for 0.025, 0.1, and so on, right? So in other words, we have just about 6 different sides of the areas were given, right? So apparently you cannot run, it's hard to run the test using p-value approach if you're using t-table, right? Well, if you want, you can use Excel to calculate the p-value here. Okay. Maybe I didn't copy it here, yeah? But if you open up Excel, all right? In case you want to use a p-value, right? You can say equal TDIST, and open the parenthesis, and you give a critical t-value. Say in this example, your test statistic came out to be -2, right? So you can say 2.0. When it doesn't matter whether it's negative 2 or 2.0 because it's symmetric, right? 2.00, comma, and degrees of freedom 63, comma, and the last parameter here is tails. Whether you have to tell the computer whether you're running one tail test or two tail test. Okay? So if you're running two tail test, type 2 here, right? And you don't have to close the parentheses usually, right? Just enter. Oh, computer is very slow. Yeah, so that p-value came out to be 0.0498, almost 0.05. Okay? But still, it's less than 0.05, right? So you can make a conclusion based on that value. Again, the formula is t-dist, t-dist, and you just specify your test statistic and the degrees of freedom and whether you're running one tail or two tail test. Okay? Well, just for fun of it, what if you were running a one tail test here? If you're running one tail test, that becomes 0.249. Okay? Okay. And let me just explain this and I'll let you go today. So, if you were running two tail test, you will have your rejection region on both sides, right? And that's half of alpha. Okay? And when you have your test statistic, okay, and you're going to have half of p here, negative test statistic, right? And negative half of p here, right? So you're comparing half of p to half of alpha, right? So in order to decide whether you should reject the null hypothesis or not, right? Or in the other way, to find out whether test statistic exceeds the critical value or not, right? You're comparing half of p to half of alpha, right? And if this is less than that, then you're going to reject the null hypothesis, which means the same thing as if p is less than alpha, right? You're going to be rejecting the null hypothesis, right? Well, if you're running one tail test, though, things are slightly different, right? If you're running one tail test, you have only the rejection region on only one side, right? And so if you want to be 95% confident, right, then you're going to set aside the entire 0.05 on one tail, right, depending on your alternative hypothesis, right? So if you are running in this test, suppose you want to find out whether it's actually longer than 375 hours, right? Right? So your alternative hypothesis is greater than 375, right? Then you're going to set up the rejection region here on upper tail only, and you're going to have entire 5% type 1 probability of type 1 error on that side, right? So in that case, if your test statistic comes out to be here, okay, that's half of p, right? Because you're going to have another half of p here, right? So you're going to be comparing half of p to entire alpha. And if the half of p is less than alpha, you will reject the null hypothesis. right? That's the difference, right? So many times I suggest you, instead of doing this, just say, if you're running one-tail test, right? Your decision rule should be reject the null hypothesis if P is less than 2 alpha, 2 times alpha. Because calculation, this is easier, right? Because alpha level is usually like something like 0.01 or 0.05 or 0.025. It's easy to multiply by 2, right? But your p-value can be something like 0.2179, right? And if you want to divide it by 2, you'll have to use your calculator, right? So instead of doing this, right, just use this rule, right? And you can easily make the decision, right? All right, if you don't understand it completely, well, we're going to have an opportunity to do some practice in the beginning of Thursday's class. Any question? All right, I'll see you on Thursday.